Hello everyone, this is Fatima Zohra NOUASRIA speaking, and today I am going to represent my work on the synthesis and characterization of pure and doped zinc oxide thin films. The outline of the presentation is as follows. First, this work is started with a brief introduction on metal oxide semiconductors and their applications. Then, we're going to show you how zinc oxide thin films were elaborated, and in the end of our presentation, we're going to discuss the obtained results and summarize it in a conclusion. In recent years, semiconductors have attracted the attention of researchers because of their extensive applications in many fields as optoelectronics and photovoltaic applications. Currently, the vast majority of solar cells on the marketplace are silicon-based, which still achieve the highest performance. However, the technology involved in producing a silicon module has matured to the extent. Also, the strict requirements for material purity results in high material and fabrication costs. Therefore, less cost and more abundant alternatives to these solar cells remain elusive but highly desirable in the marketplace. Cheaper photovoltaic cells can be produced by using non-polluting, abundant materials with low manufacturing process. This is where the metal oxides offers promising potential as an alternative photovoltaic technology. Zinc oxide is an N-type metal oxide semiconductor with a direct band gap, an abundant, stable, and non-toxic material, and presents a high transmission in the visible region. These properties make it promising material for manufacturing heterojunction solar cells. Electrodeposition is one of the most interesting methods for the synthesis of thin films of semiconductor oxides because of its low cost and environmentally friendly approach, ambient pressure processing, low temperature synthesis. Several literature studies have confirmed that doping zinc oxide nanocrystals modifies its electrical and optical properties. In particular, copper is considered an interesting dopant due to its low cost, and it has many chemical and physical characteristics similar to those of zinc. This work aims to optimize the properties of zinc oxide thin films as a window layer by doping with copper ions for p-n junction solar cell applications. Electrodeposition of zinc oxide thin films was performed on an ETO-coated glass substrate using standard 3 electrode. The thin films were deposited from aqueous solution containing potassium chloride, hydrogen peroxide, and zinc chloride at 65 degrees. We move now to the results. This figure shows the linear voltammograms response of zinc oxide growth solution with different amounts of copper. As can be seen, all the voltammograms shows the same appearance, where an obvious cathodic current started to flow near minus 0.6 volt, which was attributed to the reduction process of hydrogen peroxide. It was observed that introducing copper doping, the cathodic current tended to increase. This revealed the increase of the reduction rate of hydroxide ions, which in turn leads to an increase in the growth rate of copper-doped zinc oxide nanostructures. The crystallographic structure of pure and copper-doped zinc oxide was investigated by Xray diffraction. As can be seen, the sharp and intense peaks correspond to the weirdest phase of zinc oxide, reveals the high crystallinity of the samples. The XRD spectrum shows a preferential orientation along the 002 plane, suggesting that the crystalline grains are mainly oriented along the C-axis. The intensity of peaks decreases with increasing copper concentration, which can be explained by the slightly smaller ionic radii of copper compared to zinc ions. The crystalline size of the electrodeposited zinc oxide was calculated using the full width at half maximum of the 002 peak according to the Xray formula. A decrease in the crystalline size with copper doping is observed, which is due to the appearance of new small crystallines, where the substitution of zinc ions with copper ions create shorter bonds. The surface morphology of the synthesized samples are revealed by the SEM observations. In the absence of copper ions, the surface of zinc oxide appears as a flat surface consisting of uniform and closed hexagonal nanorods packed against each other. Up to 0.2% smaller diameter nanorod is observed, while from 0.5% the diameter of the nanorod appears to increase slightly, giving rise to popcorn-like structures for samples doped with 1%. The influence of copper doping on the transmission and the band gap of the zinc oxide samples was studied by UV visible spectrophotometry. It is clear that doped zinc oxide exhibits a gradual shift toward the longer wavelength side compared to pure zinc oxide. The transmission value increases to a maximum value of 86% for samples doped with 0.1%. The highest transmission value obtained for doped samples can therefore be considered a preferable material for thin film solar cells applications, as they require the use of materials with high optical transparency properties. The band gap energy estimated from the dot plot shows that when the copper content increases, the band gap value decreases from 3.36 to 3.02 electron volts. To determine the presence of copper in the doped zinc oxide, XPS measurements were performed. From the survey spectrum, additional peaks characteristic of copper are observed for doped samples, confirming the presence of copper elements in the doped zinc oxide. High-resolution spectra of core level of copper is shown. According to the literature, the copper species detected in our samples are in monovalent state. Science solar cells are applications based on the excitation of electrons in a semiconductor material using a light source. Thus, in this part, we represent the photoelectric response under and without elimination of our films by photoelectrochemical study. As shown, under UV elimination, the photocurrent response showed a tendency to increase through the contribution of copper doping, where the improvement was more than 10 times greater for samples doped with 0.1% compared to pure zinc oxide. Finally, in this work we investigated the morphological, structural, optical, and photoelectrochemical properties of zinc oxide thin films deposited by electrodeposition technique doped with the different amount of copper. The XRD spectrum shows a preferential orientation along the 002 plane. The intensity of peaks decreases with increasing copper concentration. SEM images shows changes in the morphology of the nanostructures after copper doping. According to the optical measurements, doped samples displayed a redshift in the visible light region as the copper content increases. Optical band gap of the films was found to decrease. The inclusion of copper doping greatly enhanced the optoelectronic properties of zinc oxide films. Such behavior provided a direct evidence to support the fact that the inclusion of copper doping could be an efficient way to improve the performance of zinc oxide as window layer for PN heterojunction-based solar cells applications. Thank you for your attention.